Swayam Prabha. Digital India. Educated India.
Integers are going to show up in this form, right? Zero will show up in many numbers, but all of these numbers that I get, they are all distinct numbers because there are no leading zeros. So some number like 112 and 11, they're they're all different integers, right? So just reading them as integers, so that you can explicitly write this in terms of multiplying by powers of 26 and 27 and adding them together. They're all distinct integers. There are no two equal integers unless the two strings are equal, right? If I give you two strings, even if the strings are varying lengths. And here it was important to omit the leading zeros because otherwise there would be two strings, one longer than the other simply because it's padded with leading zeros, which would both give you the same integer. But since I'm considering strings which do not have zero in them, these strings all map to distinct integers. So this is an injective function. It's not a bijection because I'm omitting all those. I'm never going to hit all those integers which have zero in their base 27 representation. Okay, so this is an injective function from S1. But this is good enough because I'm going to apply CSB theorem. For that, I need an injective function in the reverse direction also. And that's trivial. I mean, you can do many things, but here I'm just going to map an integer n to a string of length n consisting of n a's. Okay, so clearly there's one-to-one. So now I have one-to-one functions going both ways. So so by the CSB theorem, the X is a bijection from S to the set of natural numbers. Here's one more example. I'm going to define the set T to be the set of all infinitely long binary strings. So what's an infinitely long binary string? For each position in that string, the bit is specified. So you could think of it as a function from the set of our positions, namely set of our natural numbers, to bits. Okay, so that's an infinite binary string. Each object, each such string is an infinite object, and now I'm going to consider the set of all such infinite strings. How big is the set? I'm claiming that this set is as big as the set of real numbers. That is to say, the cardinality of the set is the same as the cardinality of the set of real numbers. Okay, so I'm claiming that there's a bijection between these two sets. How do I prove that? I'm going to use the CSB theorem. So I'm just going to give injective functions going both ways. So in one direction, that the set T has an injective function into the set of real numbers. Here is a function. So I would take a string in T. So it's an infinite string number. So let's say the string is S1, S2, S3, and so forth. I would interpret this as a real number that I can obtain by writing it as 0. So these are all bits, right? S1, S2, S3, they're all bits. So it's each bit is a 0 or a 1. So there's an number of the form 0.00100, right? But I'm going to interpret this as a real number in decimal, okay, to the base 10. Okay. I'm claiming that this is a one-to-one mapping. That is to say, if I took two different strings, so they differ at some position, right? Say they differ in the first position, for instance, 0.1 1 something and 0.0 something. So then there's a finite difference between the real numbers. There's at least there's a lower bound on how close these two things can come. So 0.10, even if it is 0.10, and the other one is 0.01. So remember, we only have zeros and ones in the string. So even if one of them is 0.1111 and the other is 0.1000, um, there's a substantial difference between the two, right? In particular, it's at least 0.05 away. So these are two different real numbers because there's a finite gap between them. So that's why there's a one-to-one mapping. Any 2-bit strings, here I consider 2-bit strings that differ at the first position, but in general they differ at some position, and then I can get a gap between the real numbers they map to. So here it was important that I interpreted this bit string as a number written not to the base 2, but to some larger base. If I had treated it as binary, then the two strings, 0, 1, 1, 1, 1 and 1, 0, 0, 0, so they are two different strings for sure, but they both map to, so this is 0.1, right, which is basically half in binary. And this thing is also half. This is 1/4 plus 1/8 plus so forth. It's an infinite sequence, which also corresponds to the real number half. So these would have had no gap between them. Okay? The difference between them would have been 0.0000. So, but I can easily avoid that by treating this bit string as a number written in, say, decimal or any higher base higher than 2. Okay, so this is my injective function in one direction, and in the other direction I could, well, so real numbers go from all the way minus infinity to plus infinity. So first thing I could do is just injectively map this entire real number line into a smaller interval, say 0, 1. And this I can do even very nicely using a continuous function, say 1 over 1 plus e to the minus x. You can convince yourself. It maps the entire real line into this interval 0, 1. So it's an injective mapping. And then I further map this interval 0, 1 into a string in its binary, the string that corresponds to its binary expansion, right? So there is a canonical representation of every real number as a bit string. Okay, so there are two representations in its binary expansion, say in these two cases. We will take one of them as the canonical one, say this one. So every real number can be uniquely mapped to a bit string in this way. And clearly, if two real numbers are different, they will be mapped to two different bit strings. Okay? So same real number could have been mapped to two bit strings, but we chose one of them. But two real numbers will be mapped to two different bit strings. Okay, so this is an injective function. So now again we have injective functions going both ways. So the cardinality of t is less than or equal to cardinality of r, and vice versa. So by the CSB theorem, the cardinalities are equal. Okay. As a corollary, so this looks a little bit like what we argued for integers or natural numbers, that two, or for countable numbers in countable sets in general, that the cross product of two sets, say in the case of n, it was n cross n, has the same cardinality as n. But here, this R is not a countable. We shall shortly see that R is not a countable set. Nevertheless, R cross R has the same cardinality as R. Okay, so we are talking about, so think of this as a plane, and this is a line. So it's a little counterintuitive that the plane has as many points, or the cardinality of the set of points in the plane is the same as the set of cardinality of the set of points in the line. But you can you don't have to think of it as in terms of areas or space filling curves, which you could, by the way. But here, all you need to do is get some bijection. It doesn't have to be a continuous map. Some bijection between these two sets. And since we already established that the set of real numbers has the same cardinality as a set of this set T, set of infinitely long binary strings, what you need to show is only that T squared has the same cardinality as T, okay? And that is easy to see, and a bijection from between T squared and T would be to take two infinitely long bit strings and interleave their bits, right? And you will get a single infinitely long bit string. And it's a bijective function because you can go back by taking the odd bits and the even bits separately into, so you can separate out one infinitely long bit string into two infinitely long bit strings to reverse this operation. Okay, so this is a one-to-one mapping, and its inverse is also one-to-one. So it's a bijective mapping. So therefore, T square and T have the same cardinality. So here we are actually explicitly giving a bijection instead of using the CSB theorem. Okay? And then combined with the fact that T and R have bijection between them, you get that therefore R square and T square have bijection between them coordinate wise. So R square and T have a bijection between them, okay? Which in turn has a bijection with R. So R square and R have a bijection between them. Okay. So to summarize things we said so far, so we defined this notion of equality of cardinalities as two sets of equal cardinality if there is a bijection between them. We defined that set A has a cardinality less than or equal to cardinality of B if there is a one-to-one function, an injective function from A to B. And you can see that it's essentially the same as saying that there is an onto function from B to A. So in particular, if there is an injective function from A to B, what you can do is you can convert that, you can consider the inverse of that and then fill up the positions that were not in the image of A arbitrarily to get an onto function from B to A. And conversely, if you have an onto function from B to A, then you can essentially reverse it, but then there will be each element in A could potentially be mapped to multiple different elements in B, so you arbitrarily choose one of them. So technically, to do this, to go back and forth between an injective function from A to B to an onto function from B to A or vice versa, you need to rely on something called the axiom of choice, which is a very natural axiom saying that when you have um, several sets, non-empty sets, you can choose one element from each of those sets. Um, but it turns out it's, it needs to be put in as an axiom into the set theory. It doesn't follow from other natural axioms you would have in set theory, set theory formalization. So, without getting into the formal foundations of set theory, you can just take it for granted that you can, do this, so that you can. So these are equivalent statements, that there is a one-to-one function from A to B is the same as saying there is an onto function from B to A. Okay, so all I just wanted to point out is that though we defined cardinality of A less than or equal to cardinality of B using one-to-one functions in one direction, you could define it in terms of onto functions in the other direction. And we saw this CSB theorem that if both these conditions hold, then A and B have the same cardinality. And we defined countably infinite as having the same cardinality as a set of integers. Okay, and we saw some examples. And what I'm going to do next is look at uncountable functions. So what is an uncountable function? It's an infinite function which is not, sorry, infinite set. So what's an uncountable set? It's an infinite set which is not countably infinite. Okay, so it is beyond being countable. Okay, so there is no function, there's no injective function from A to the set of natural numbers. So you cannot assign natural numbers to each element in A. Okay, or from what I was just talking about, you could also reinterpret it as saying there is no onto function from integers to A. So, so this is closer to the way I said you cannot assign an integer to every, or rather, you want to number the elements in A. You want to make sure all the numbers, all the elements get a distinct number. It's okay if some elements get multiple numbers. Okay, you'd like to just or you could think of it as some numbers are not used because there are other numbers that are used to number an element. So either way, you could think of it as numbering elements in A, so that is counting elements in A, possibly in a superfluous way. Same, some integers are not used, or alternately some elements get multiple integers. Okay, so that corresponds to being countable. Being uncountable says there is no such assignment, so no onto function from N to A. You'll have to miss some elements in A. Okay. So we are going to use this formalization to say that, to prove that some sets are uncountable. Okay. And the most natural set you would expect to be uncountable is a set of real numbers. Okay. So we will see a proof that the set of real numbers is uncountable. We'll see a few related claims using which we'll actually get to this uncountability of real numbers. And so remember, we defined the set T as a set of all infinitely long binary strings. That turns out to be uncountable. Okay, so in contrast, if I looked at the set of finitely long binary strings, there are, so all binary strings of length 0, length 1, length 2, and so forth. There are infinitely many such strings, but that set is easily seen to be countable. I can, kind of lexicographically sort all these finite strings say the shorter ones are first. And so every finite string gets a number in this lexicographic ordering. So that set is countable. What I'm claiming is that the set T is uncountable. Okay? And we already saw T and R have the same cardinality, so that would establish that R is uncountable. Okay? So how do we see T is uncountable? We actually will relate T to another set. There's a power set of the set of natural numbers. So remember, the power set of a set consists of all the subsets of that set. So Pn consists of all sets of integers, potentially infinite sets of integers. So for instance, the set of all even positive even integers is an element in the power set of n. N itself is an element in the power set of n. The empty set is an element in the power set of n. There are finite sets, there are infinite sets, all as elements of power set of n. And I'm claiming that this power set of n is actually uncountable. Okay, it might look like it's a very discrete object, right? So n itself is a discrete object, and then we are just going around picking subsets of n. So it's a very discrete kind of set, but we shall see that this is uncountable. And it's not really hard to see actually the set power set of n it has a bijection with the set T. Okay, so what is that bijection? So remember, an element in T, an infinitely long bit string, you could think of it as assigning for each position I some value Si. Si is either 0 or 1. Okay, that's what a string S, an infinitely long bit string S is doing. For every position I, it's assigning a value 0 or 1 to I, so call that S sub I here. And what you could do is you can use this assignment to define a subset. So natural way to do that would be to define the set of all the positions where Si is 1. Okay, so there's a subset of all the integers, all the positions, 0, 1 up to infinity. And the subset itself could be finite, could be empty, could be all of n, it could be infinite. It's some subset, right? And so I'm going to define this function which takes a string and maps it to this subset of natural numbers, okay? And I'm claiming that there's a bijection. If I took two different bit strings, they differ in some position, that would make sure that the set I get, so they differ, one of them has 1 and the other has 0. So exactly one of those sets will have the element I being the position where the two strings differ. So exactly one of those strings will be mapped to a set which contains I, and the other will be mapped to a set which does not contain I. So those two sets cannot be the same. So it's injective, and it's onto also, right? Every set can be, you can, given an arbitrary set, you can define the corresponding bit string such that that bit string will be mapped to that set simply by saying that the bit string equals 1 at all those positions which belong to the given subset. Okay, so you should convince yourself that there's a bijection between T and the power set of n. So by what we're going to do is we'll show that Pn is uncountable, and that would establish that T is uncountable, and therefore R is uncountable. Okay. All right. So now, how do we show Pn is uncountable? Okay. Yeah. By the way, this was the explanation of what this bijection between T and Pn is doing. Okay, so how do we show something is not countable? And there's a remarkable, seemingly simple, but uh, very counterintuitive, at least at the first sight, um, argument which can be used to show that something is not counted. Okay, so let's actually see this. It's a small, short proof. It's in a slide. Okay, I'm going to prove that the power set of natural numbers is uncountable. So I'm going to show that no function is going to be, no function from n to Pn can be onto. Okay? There is no way to cover all of Pn using um, integers. Okay, that's what I would like to prove. Okay, so take any function f, and at the end of the slide we'll say that f is not onto. Now it's a function from n to Pn means for each value of element in n, 0, 1, 2, 3, and so forth, I can write down some element in Pn. How do I write down an element in Pn? So an element in Pn is a subset of n. So I'm actually going to use the representation we just now talked about as an infinite bit string. So imagine the columns here, imagine this table where the columns are indexed by 0, 1, 2, 3, the natural numbers. And I put a 1 in a, F0, the first position is 1 because 0 is in this set, F0. And 1, 2 are not in the set, 3 is in the set, 4, 5, 6 are not in the set, and so forth, right? So a set, so F0 is a set, is being represented using this infinite bit string. Okay, so now I stack all these bit strings together in a table. So this table in the ijth position, I have a 1, if and only if, so I is the row index, if and only if j is contained in the set fi. Okay, so that's a well-defined set. So given any function f, I can define this table, which is just a function that maps to natural numbers to a bit 0 or 1 using this condition. Okay, so consider this table. And Cantor's diagonal slash, as the name indicates, looks at the diagonal of this table. Okay, so there's a diagonal where we are looking at whether 0 is in F0, whether 1 is in F1, and so forth. So whether I is in Fi, right? That's what the diagonal, the ith element in the diagonal tells you. And I'm going to take this diagonal and flip it. Okay, so the diagonal went 1, 0, 1, 1, 0, 0, 0. The flip diagonal goes 0, 1, 0, 0, 1, 1, 1. Okay, so I just flipped every position in the diagonal. So I get an infinite bit string. Now I ask, so it's a this bit string corresponds to a set, right? So let's call that set X. Okay, so X in this example does not have 0 in it, has 1 in it, does not have 2, 3, has 4, 5, 6, and so forth. Okay, so it's some subset of natural numbers. Okay, so formally, what does that? What is the set? It consists of all elements j, such that in the flipped position it has to be 1. So in the original position it's 0. So tjj equals 0. That's when x contains j. Okay? And what does it mean for tjj to be equal to 0? It means that j is not in fj. Okay, so x consists of all j such that j is not in fj, where f is this function, this arbitrary function we are given that maps integers to subsets of integers. Okay, now so far so good. Now here is a magical bit. I ask, where in this table can this set X appear as a row? Okay. So this row, does it appear in this table anywhere as a row? Well, it cannot appear in this table. Why can't it appear in this table? Because say it were to appear here as a 4, you look at the fourth position. The X has a 1 there, whereas here it's a 0. And it's bound to be the opposite of whatever the fourth element is, right? So this row disagrees with the ith, with fi at the ith column. For every I, it disagrees with f of I at the ith column. Okay, so it cannot be any of these rows because for every row there is at least one position where this the set X disagrees with the set in that row. So X cannot appear as a row in this table. What does that mean? That means F is not onto. To be onto, every subset should show up as f of I for some I. Okay. So since this set cannot show up as f of I for any I, this cannot appear as a row in this table. Just kind of kind of a clever X that we picked. So it's showing that this one X cannot occur. But clearly, if it were just this one X that was not in this table, we could have just shifted the entire table down and put this X, at the top of the table. That's not the case, right? So give me any F. I will tell you there is one there is at least one X that's missing, but in fact, there are going to be an infinite number of X's that are missing. In fact, an uncountably many X's that are going to be missing from this table. But to prove that Pn is uncountable, it suffices to show that for every function, there is at least one X that is not in the image of that function. So F is not on. And this is actually a nice argument that extends to saying that not just that, so what we just now showed is that Pn is not equal to, cardinality of Pn is not equal to cardinality of n, but actually this extends to any set A. So there is no onto function from A to the power set of A for any set A. So for finite sets, it's clear. This has, n elements. This has 2 to the n elements. So you cannot have an onto function from something which has n elements to something which has 2 to the n elements. But for infinite sets, we need to go through this proof. Now we cannot exactly go through this proof because there's a little bit of something we used about the set A being integers. We talked about building a table, right? So if you think what we mean by a table is that there are rows, then the rows are countable, right? The first row, second row, third row, and so forth. So the rows were indexed by natural numbers, which you cannot do when if A itself is uncountable, right? If A were the set of real numbers, to prove that the power set of real numbers has a larger cardinality than the set of real numbers, you cannot talk about a table enumerating this function from real numbers to something. You cannot list all the real numbers as rows in a table. But actually, we don't need to. We can directly skip. This kind of diagonal was a nice visualization, but you can directly skip to the formal definition of what the set X was. So X was defined as set of all j such that j is not contained in f of j. That definition we can still use. So I'm going to go ahead and think of X as the subset of A such that consisting of all the elements J such that J is not an f of J. Okay, and then this diagonal argument that we had that X doesn't appear in this table still holds. So what I'm claiming is that there is no there's no element I in this set A such that X appears as f of I. Okay, so I'm not making any assumptions about this being a table or there being, A being countable. How do I prove this? That you cannot have I such that X equals f of I. So just like here, we did by contradiction, right? We said, or we got a contradiction by looking at the diagonal element, and it differed. F of I and X differed in the diagonal element. So, so here, again we'll prove by contradiction. So suppose, for the sake of contradiction, there is an I such that X equals f of I. Let's go and look at the whether I is in X or not. So if I is in X, then by definition of X, right? X is f of I is in f of I. But by definition of X, if I is in f of I, then I is not in X. X consists of exactly those elements I such that I is not in f of I. So if I is in f of I is not in X. So if I is in X, then I is not in X, and that's a contradiction. I mean, and conversely, if I not in X, then I has to be in f of I, and then I has to be in X, by using this definition. So here in this part, I'm using the fact that X equal to f of I, and here I'm using the definition of X, right? So so I is in X if and only if I is not in X, and that's a contradiction. So there cannot be an I such that X equals f of I. Okay? So there is no onto function. So to summarize and to go back to the claim about real numbers, so what we just now saw is that there is no onto function. In particular, Pn is not equal to, the cardinality of Pn is not equal to cardinality of n. You could say that the cardinality of Pn is, if you want, or you could say cardinality of n is strictly less than the cardinality of Pn. Okay? Instead of being less than or equal to, because they are not equal. And we already saw this connection that T has the same cardinality as P of n via an easy explicit bijection, and that T and R have the same cardinality via the CSB theorem by giving injections in both directions. So therefore, you cannot have R have the same cardinality as n, because if you did, then R has the same cardinality as P which has the same cardinality as Pn, but cardinality of Pn cannot be equal to cardinality of n. So you'll get a contradiction if R has the same cardinality as n. So R does not have the same cardinality as n. It is infinite. In fact, n cardinality of n is less than or equal to cardinality of R. So R is infinite and is not countable, so it's called uncountable. So just, it's worth thinking about this for a second, right? So the cardinality of n is infinity, but the cardinality of R is a higher infinity. Whereas, cardinality of n square is not a higher infinity, the same infinity as cardinality of n. And similarly, cardinality of R square is not a higher infinity than cardinality of R. Okay? But going from n to R, or n to power set of n, you step from one level of infinity to a higher infinity. Okay, and now you could go even further. You could take the set of real numbers, or the set of the power set of n, and take its power set, and you will get, you know, an even higher um, level of infinity. Okay? So in fact, these levels of infinity, these cardinalities, have names. Uh, they're called LF0, LF1. So LF0 is a set of, is a cardinality of natural numbers, so that's a countable infinity. LF1 is a set, is a cardinality of uh, P of n or of R. LF2 is a cardinality of the power set of R and so forth. Okay? Um, and there's a fascinating, you know, deep line of work trying to understand um, these levels of infinity, and whether there are intermediate infinities. The short answer is no. You know, you can think of just these as levels of infinities, and there are no intermediate infinities. But this is actually not quite the full story. You can have a system where there are intermediate infinities. So this again goes down to the foundations of set theory, and how you define, or what axioms you choose to use to define your set theory. So we'll not get into that, but it's important from a discrete mathematics point of view, or from a computer science point of view. Uncountability is important to know about, because you will encounter it in talking about undecidability, uncomputability. So we'll not get into that in this course, but that's something you will see in future courses.